My name is Pavitran. I am going to speak on the topic simple cubic unit cell. The simple cubic unit cell is a cube with an atom at each corner of the unit cell. The unit cell completely describes the structure of the solid, which can be recognized as almost endless repetition of the unit cell. The volume of the unit cell is readily calculated from its shape and dimension. This calculation is particularly easy for a unit cell that is cubic. The dimension of the unit cell are dictated by the size of the atoms in the cell. In case of simple cubic unit cell, the atoms lying on a corner is in contact with each atom on a neighboring corner. Thus, the side of the unit cell has a length 2r, where r is the radius of an atom. Atoms, of course, do not have well-defined bounds. Thus, the radius of an atom is somewhat ambiguous. In the context of crystal structure, the diameter 2r of an atom can be defined as the center to center distance between the two atoms packed as tightly together as possible. The density of the solid is the mass of all the atoms in the unit cell divided by the volume of the unit cell. Thank you.
Hello friends, I am Vishwateja from Carpe Diem batch. Today I am going to say about cubic primitive unit cell. Before going to that concept, I would like to say about crystal lattices and unit cells. What is a crystal lattice? Any crystalline solid will consist of a regular repeating pattern of constituent particles. These constituent particles are known as crystal lattices. For example, see this diagram. This particular arrangement of these particles are known as crystal lattice. And what is a unit cell? As many of you have doubt, unit cell is a primitive structure, is the smallest portion of the crystal lattice. So we can define a unit cell as the smallest portion of the crystal lattice, in which if we repeat this smallest portion, we will get to go to a solid. And let me say there are two unit cells, two types of unit cells. They are primitive unit cells and centered unit cells. Now my concept is to say about primitive unit cell. In this primitive unit cell there is only one concept, that is a cubic primitive unit cell, which will be as this shape, as a simple cube. Pardon my drawing, but it will just look like a simple cube. The atoms on this cube will be arranged on 8 corners as shown. Let me show you the file. Yes, like this. The atoms will be arranged in such a format. There are 8 atoms in 8 edges of each cube. Okay, this will be much clearer. This is a primitive atom. These atoms of each radius as I've set it default as 5 centimeters. The sphere, this atom will be arranged in 8 on 8 edges of the cube as shown. Okay. Now there are 14 types of bravais lattices, as primitive, body centered, face centered, and there are 14 types as you can see in this diagram: edge centered and hexagonal, like and so. Now what is packing efficiency? A packing efficiency of this cubic simple lattice, as you can see in this diagram, this side of each cube consists of, this is the radius of one atom and this is the radius of other atom. This 2r compresses of one side of a cube, means a is equal to 2r in this case. This is the same thing that we have written here, a is equal to 2r. the volume of a cubic unit cell as a volume a cube, as side of the unit cell is a, as mentioned above. And what is the as radius of this single side of a unit cell is r, sorry, a, and it consists of 2r. Each volume of each sphere is found to be 4 pi r cube, as we know. And to find the packing efficiency, it is volume of one atom to the divided by volume of a cubic unit cell into 100, as volume of one atom is 4 pi r cube as found here, and volume of a cubic unit cell is 8 r cube, as we got a relation as a is equal to 2r, and we have to relate a and r so that the terms would cancel. It's a simple calculation. 4 pi r cube by 8 r cube into 100 is equal to 52.4%. Hence the packing efficiency of this primitive unit cell is found to be 52.4%. Well, that's all. Thank you. Okay.
Hello guys, today I shall be talking about body-centered cubic unit cell. So a body-centered cubic unit cell's specialty, apart from the simple cubic unit cell, is the fact that it has one atom at the center of the unit cell. So but lattice wise it is the same as cubic unit cell, except for the fact that it has one atom in the center. So it looks like this. So it seems to be having a total of 9 atoms, 4 at the top and 4 at the bottom, and 1 atom in the center. But in reality it is actually not made up of 9 atoms. The fact is that these spheres at the top and bottom are being shared by other unit cells also. So now let's find out the number of atoms this particular unit cell is made of. So this involves a very simple mathematical calculation. So let's see how it is calculated. So now let's imagine that we join the centers of the sphere. So let's try doing that here. Yes. So as we keep joining the centers of the sphere, we get a rough figure like this. So this has been drawn neatly in the next figure C, and you can see that the only atom that is completely covered or that is completely enclosed by the sphere is the atom at the center. So the corners are actually made up of sections of the sphere. So if we actually try and find out what portion of the sphere is this section made of, it's a very simple calculation. So we can mathematically say that this particular section that you can see here is approximately, or rather is equal to 1/8 the volume of a sphere. So now since it's been given that it is 1/8 the volume of the sphere, we can do the calculation very easily. So there are totally 8 corners in a sphere, and the volume that is comprised by one of the corner is approximately, or is rather equal to 1/8 per corner atom. So when you multiply 8 into 1/8, we get 1 atom, and that is 1 atom that is completely enclosed by the cube. So which makes it 1 into 1, that's equal to 1. So totally there are 2 atoms. So often in our high school calculations, we might be interested in knowing the packing efficiency, or rather to find out how much of space has been occupied inside this cubic unit cell. So let's try to find out the packing efficiency of this particular lattice. So again, the calculation for this is a very simple one. So now let's try to calculate the length of the diagonal of this particular cube that we see. So if we try to calculate the length of the diagonal, we can say that it is equal to √3. This is a very simple calculation. First we have to use the Pythagoras theorem to calculate the diagonal of the square EFCD, which will be equal to root 2, and using this as a base we can calculate the hypotenuse of the whole cube, again with the same Pythagoras theorem. So this is a rather very simple calculation, and we can easily find out that the diagonal's length is equal to root 3. So now we can also think about alternate ways to calculate the length of the diagonal. So can we express the length of the diagonal in terms of the radius of the spheres? So now let's go back to the picture that we saw previously. So in this particular picture, you can see that the diagonal starts from here and it somehow comes till here, correct? So if we now choose to start, say for example, we want to travel from this corner of the cube to this corner of the cube. Let's see the amount of distance that we have to travel. Let's imagine this. So the first step I have to do is to first travel r distance from this corner of the sphere, and now to pass this particular sphere I have to travel 2r. So now let's note it down. So from here to here we have to travel r, and from and to cross this big sphere we have to travel 2r, or rather the diameter of that sphere, that is 2r. And finally from this particular end point of the diameter to this corner we have to travel an r. So this gives a total of 4r, correct? So now but we also know that this 4r is same as the diagonal of this cube. So the diagonal of this cube is equal to root 3 here. Pardon my handwriting still. So so we get this particular equation, that is root 3a is equal to 4r, by imagining that we are going to travel from one corner of the cube to another corner that is placed diagonally. So now the packing efficiency's definition is again a very simple one. It is the volume occupied by two spheres in the unit cell. Why do we say two spheres here? Because we just saw that this BCC structure is same as the volume of two atoms. So that's why we say volume of two spheres in the unit cell into 100 is to find out the percentage, divided by the total volume of the unit cell. So now the total volume of this unit cell is a very simple calculation. It's just going to be a cube, that is the volume of the cube, a cube. So now the calculation is going to be pretty simple from here. So 2 into 4 by 3 pi r cube. 4 by 3 pi r cube is the volume of sphere. So 2 times the volume is going to be 2 into this divided by a cube. So when you want to divide it by a cube, so a cube. So now but we also know a can also be written as 4r by root 3. So we are going to substitute 4r by root 3 instead of a. So this gives us this particular calculation. So upon solving we get the packing efficiency to be 68%.
I am Vishal. I am going to tell about the crystal of body cubic center. In this type of unit cell, the constituent particle occupy 8 corner and 1 atom from the center. So the total number of unit cell is equal to 1 upon 8 into 8 corners plus 1 atom from center, that is 2. That is total number of unit atom in body center is 2. Now we find the atomic packing fraction for BCC. We know atomic packing fractions is equal to volume of sphere inside unit cell divided by volume of unit cell. For volume of sphere inside unit cell equal to 4 divided by 3 pi r cube, and volume of unit cell is equal to a cube. Now we have to find the relationship between a and r. In BCC the in BCC the relationship between a and r is equal to a equal to 4 divided by 3 root r. Now you put this value in the formula of APF, and then we get the packing fraction for BCC is 68%. That is 68%. That is, it is not closed pack. And now we find coordination number. Now we find coordination. Coordination number is and total neighboring atom. That is for BCC. Coordination number is 8. Thank you.
Hello everyone, this is Savant, and I've got the topic face-centered cubic lattice. A face-centered cubic lattice is an arrangement of atoms in a crystal in which the atom centers are disposed in space in such a way that one atom is located at each of the corners of the cube and one at the center of each face. The structure also contains the same particles in the centers of the 6 faces of the unit cell. For a, for a total of 14 identical lattice points, the face-centered cubic unit is the smallest repeating unit in a cubic closed packed structure.
Okay guys, let's get started. Now this is an FCC lattice structure which consists of 14 atoms. Elements such as gold and silver crystallize to form this structure over here. Now the packing fraction of this is around 74%. So let's get straight into the formulas. To find out the effective number of atoms, to find out the packing fraction, we need to find the effective number of atoms first. So now there are 4 effective atoms in total for an FCC lattice. Now this is due to 8 atoms in the corner and 6 atoms at the faces. Now each corner atom provides only 1/8 of an atom, while every atom at the center of the face provides half of an atom. This is 1/8 of an atom, while this is 1/2 of an atom. Now using Pythagoras theorem, we get root 2 of L, which is the length of a cube, is equal to 4 times R, which is the radius of the atom. Now the closest you can get is at each side, where 3 atoms without no space are joined over here. So 4 radii, that is 2 from each of the corners, and the whole diameter from the center face is taken, and using Pythagoras theorem we get that 4 times of R is root 2 times of L, as said before. Hence we know the packing fraction formula, which is the number of effective atoms, which is 4 in this case, into the volume of one sphere divided by the volume of the cube. This is the expanded formula over here, and from this relation we get that the packing fraction is around 74%.
Hi everyone, I'm Vivek and I'm going to explain about orthorhombic primitive lattice structure. Orthorhombic structure is a structure in which the axis, all the axes are of unequal distances, and the angle between each of them is 90 degrees. There are 4 types of orthorhombic structures. Those are primitive orthorhombic, base-centered orthorhombic, body-centered orthorhombic, and face-centered orthorhombic. The one you're watching is just primitive orthorhombic structure. As you can see, the sides are of different lengths, and the angle between each axis is 90 degrees. So this is called So this is called primitive orthorhombic structure. Thank you.
My name is MS Lokishwaran and my registration number is 16BME1225. I am going to explain about orthorhombic base centered cell. In this type of cell, all the sides are unequal and the angle between the sides are equal, that is 90 degree. In this cell, all the atoms are present at the corners and two atoms are present at the face centers. And example for this type of lattices are potassium nitrate, barium sulfate, etc. And the volume of the lattice is given by A into B into C.
This is the orthorhombic face-centered cubic unit cell. Its all the sides are unequal, that is A is not equals to B, not equals to C. But all the angles between them is equals to 90 degree. So it is in the shape of a cuboid. We have coordination number 4. So we have 8 tetrahedral voids and 4 octahedral voids. The 8 tetrahedral voids are here, 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 here. Like all the 4 corners, and between this, and this atoms, the tetrahedral voids are present, and the octahedral voids are between this, and this atoms. So it's an octahedral void. Its packing fraction depends on the side of the packing fraction depends on A, B and C. So this is the figure. We have 1/8 of an atom on all the 8 corners, and the half atoms at the center of the each face. So that's how we calculate its coordination number. So it becomes 8 into 1/8 of an atom, that is 1, plus 6 into 1/3 of an atom, that is 3. So its coordination number is 4. This kind of structure is made by gallium, and so my name is Divyesh Anand. My registration number is 16BME1179.
Hi guys, my name is Onkar and my registration number is 16BME1129. Let's talk about body-centered orthorhombic lattice system. In this system, as you see that lattice, the sides of all the lengths are unequal and the angle between these sides are 90 degree. As we know that it has a lattice point in the middle of unit cell. Some examples of orthorhombic body centered is alpha sulfur and topaz, etc.
Hello everyone, my name is Rahul Kumar Yadav and I'm a student of VIT University. Here I am going to tell you about one of the crystal structure, and the name of this particular crystal structure is tetrahedral primitive unit cell. Now if you see the structure from this view, you will be rather confused whether it is a simple cubic unit cell or a tetrahedral primitive unit cell. So let's see the relation between the side of the structure and the radius of that term, and it comes out to be that side is equal to 2 times the radius of that term. Also, if you are looking, you are getting that this looks like a square diagram. So that is why it looks like simple cubic itself when you are looking from this top view. But as soon as you are looking it from this perspective, you will be clarified that it's not simple cubic itself, because here you are getting a lot of gaps between them. So it's something which makes it different from the simple cubic itself, and the relation between the side of the structure and the radius of the atom comes out to be that side is equal to 3 times the radius of the atom, which makes it different from the simple cubic itself. So what are the facts that we get if we see this we see this tetrahedral primitive unit cell? Is that the angle between all the adjacent sides comes out to be 90 degree. Also, the packing fraction of this particular kind of structure comes out to be 35 percentage, which is uh, clearly different from the what we got in the simple game itself to be 52 percentage. So the packing fraction of this is 35 percentage. And now I would like to wind up by telling you two examples of this kind of structure. The first example of this kind of structure is silicon dioxide, and the second one is titanium dioxide. Thank you.
Hello, this is Alan Jones, and I'm here to talk about the body-centered tetragonal lattice. Body-centered tetragonal lattice, like all lattices, has lattice point at 8 corners of the unit cell, plus it has an additional point at the center of the cell. As you can see that it has an additional point at the center of the cell. That is the center of the cell right there, and you can see that in the video clearly. And moreover, the main dimensions of this one is the bottom. As you can see, the base, the two sides of the base are equal, but it's not as the same length as the breadth or height, you call it, of the lattice. The angle alpha is equals to beta is equals to gamma, which translates to every angle being 90 degree in this lattice. Now here we are going to see the front view of the lattice, followed by the left side view of the lattice, followed by the right side view of the lattice, followed by the top view of the lattice, followed by the bottom view of the lattice. Now we are seeing the isometric view of the lattice, and that's it in the body centered tetragonal lattice. Thank you guys.
Hi, my name is Russell Kaiman. My roll number is 16BME1048. I'm going to explain about the packing of a lattice structure. My type is hexagonal primitive cell, and in this type of structure, the cells are and the atoms are arranged in such a way that it's in the BAB. In this type of packing, the atoms are placed on all the 6 sides of the hexagonal structure, and 3 is placed in the center, and all the 6 are placed in the below lattice. In this type of packing, all the sides are equal, and the angles between the sides are the angle alpha and beta are equal, and that's equal to 90 degree, and the gamma angle is equals to 120 degree. The volume of this lattice is equals to root 3 by 2 a square. The example of these lattice are equals to ZNO and CDS. Thank you.
So, as we know that we have 14 bravais lattices, and these are the 14 bravais lattices, as we can see: cubic, BCC, FCC, tetragonal, orthorhombic systems, rhombohedral systems, monoclinic and triclinic. So as we know, most solids have periodic arrays of atoms which form what we call a crystal lattice. Amorphous solids and glasses are exceptions. The existence of the crystal lattice implies a degree of symmetry in the arrangement of the lattice, and the existing symmetries have been studied extensively, and a crystal structure is one of the characteristics of minerals. So these structures are known as the bravais lattices. So among these structures, today I am going to explain you the rhombohedrali centered structure. So in this hexagonal structure, we have two types: rhombohedral and hexagonal. In rhombohedral, I am going to explain you this structure, which is rhombohedrali centered structure. In this, as we can see, this rhombohedral structure, we can see there are 3 sides: A, B and C. 3 sides are A, B and C, and the angle is gamma. So here the gamma angle is 120 degree. So in this rhombohedrali centered structure, the volume is A cube root of 1 minus 3 cos square alpha plus 2 cos cube alpha. In this, A is the side of the rhombohedral cell, and the alpha is one of the angle. In this, 3 sides are A, B and C, which all the 3 sides are equal in a rhombohedral cell, and the angles are alpha, beta and gamma. Here the alpha, beta is the angles are equal to 90 degree, and the gamma angle is not equal to 90 degree, and as we have seen earlier that the gamma angle is equal to 120 degree. So now we come to the bravais lattice, that is like our rhombohedral bravais lattice. So before that, we'll see this is the rhombohedrali centered structure. So in this we can see there are 4 unit cells at the corners above, and there are 4 unit cells at the corners below, and there are 2 unit cells in this middle joining this line. Okay, so here, so this whole structure is a rhombohedrali centered structure. So now we come to the explanation. So as we can see, this is the structure, and these are the sides, that is A is equal to C and A equals to B. That means all the sides are equal, and we sometimes, like we generally denote it by HR. So a rotation axis of order 3 along the body diagonal of unit cell shown as a dashed line constrain all the sides to be of equal length and all of the angles to be equal. As we can see, all the angles are equal and all the sides are of equal length. A unit cell with these axes is referred to as primitive rhombohedral. However, instead of choosing a primitive so this basically is the primitive rhombohedral structure, this one. Okay. So now we'll go to our rhombohedrali centered structure. However, instead of choosing a primitive rhombohedral unit cell to represent this bravais lattice, it is normal to choose an equivalent rhombohedrali centered hexagonal cell as shown below. So this is our rhombohedrali centered unit cell. Okay, as we can see, there are 4 spheres, like 4 unit cells above, below, and 2 in the middle. So it is normal to choose an equivalent rhombohedrali centered hexagonal cell as shown below. Thus, the standard notation for bravais lattice of this type is HR, although a more logical notation would be RP, which is indeed sometimes used with respect to the above unit cell. So this one is normally sometimes denoted with the help of RP. So this figure shows the rhombohedrali centered hexagonal cell and its relationship to the primitive rhombohedral cell dotted lines. The 2 middle points on the dash correspond to the rhombohedral lattice centering. So these 2 unit cells which we can see are the rhombohedral centered main unit cells. So we can see more clearly here these 2 unit cells. So in this, the gamma angle as mentioned earlier also 120, and AB we can see here. So both these unit cells apply only to the rhombohedral subset of trigonal crystal system. Note that the volume of the R-centered hexagonal cell is 3 times that of primitive rhombohedral cell. So we can see these are the primitive rhombohedral cell and this one is the rhombohedral centered. So the volume for this is 3 times of this primitive one. More clearly we can see this is a primitive, so 3 times of this volume is equivalent to the rhombohedrali centered structure, which is this one. So, as we can see here, some of the examples of this rhombohedral is calcite, that is CaCO3, and cinnabar, that is HGS. So, we'll now have a look on what is calcite. So, this is our calcite. So, as we can see, this is our calcite, and the solid state structure for this is this one. So, this is the structure for our solid state structure for our calcite. And the second example we can see is cinnabar, that is HGS. So here we go to cinnabar and this is cinnabar. And the cinnabar solid state structure is this one, as we can see. So this was all about our rhombohedrali centered structure, which is one of the bravais lattice. Thank you.
Hello everyone, this is Raghavendra and I am going to talk about a monoclinic primitive cell. In crystallography, the monoclinic crystal system is one of the 7 crystal systems. A crystal system is described by 3 vectors and those 3 vectors can be shown by the highlighted blue ones there. The crystal described by the vectors is of unequal lengths as in the orthorhombic system. They form a rectangular prism with the parallelogram as its base. Hence, 2 vectors are perpendicular while the third vector meets the other 2 at the angle other than 90 degrees. So, let me show you the different views of this system. This is the, as you can see, this is the left view, And this is the front view, this is the top view, this is the bottom view, this is the side view, and this is the orthographic or the 3D view. Thank you.
Okay. Good evening. My name is Vishal and I'm part of the Carpe Diem group. And I'm here to talk about a monoclinic system. In crystallography, a monoclinic crystal system is one of 7 crystal systems. And it's part of the bravais lattice group of lattice structures. And so basically, what I've made here is a 3D model or diagram of a monoclinic base centered crystal lattice structure. As you can see, there is part of the atom on each corner of the cube, and there is one on the top and bottom on the center, which is the body centered uh, system, base centered system. Right? Take a close look. This is how it looks, and its packing efficiency is.
Now let's see what is triclinic lattice is. It is one among the 7 crystal systems which are actually differentiated based on axial length and axial angles. A, B, C are known as axial length and alpha, beta, gamma are axial angles. How they are differentiated? In triclinic lattices, A, B, C are not equal to each other and alpha, beta, gamma are not equal to each other as well as orthogonal to each other. So when we say triclinic lattices, the two things which we must remember is axial length, where A is not equal to B, B is not equal to C, and axial angle, alpha not equal to beta not equal to gamma, which is all not equal to 90 degree. So based on this, a small example, it is just a schematic representation. How can we develop a triclinic lattices? I have taken 105, 100 and 75 degree as alpha, beta, gamma, and 30, 60 and 50 as A, B, C. This is how a rough sketch looks like. So when I developed them, it showed up this way. So it is just a schematic representation and it is not an example. So this is how a tricline lattice exists. Talking about their symmetry, it is the least symmetric out of all 14 bravais lattices. Because of the two conditions, it happened so. As well, they don't have a mirror of plane, so it is much complicated. When I developed them into it just showed up this way. So it shows a perfect complex nature of it, because of which most of compounds never exhibit tricline structure. When it exhibit, it is much necessary to be that way. It has very less number of examples compared to other crystalline system, but there are two examples which are very familiar to all: potassium dichromate and boric acid. They both exhibit triclinic lattices, which are not in this manner, because it is a simple way to represent. The boric acid structures somewhat looks this way. This is how the boric acid structures looks like. It looks complex, but when you join them, when you join with an imaginary lines, you will get a triclinic structure. So This is how a triclinic lattices looks like. Thank you.
Hello, I'm Vijay Dwivedi. In this video, we're gonna discuss about defects in solid. Hope you'll enjoy.
Defects in solid are of usually two types, point defects and line defects. Point defect is due to deviation around a point or an atom in a crystal. Line defect is due to deviation in entire row of lattice point. Point defects are further classified into three types: impurity, non-stoichiometric, and stoichiometric. Impurity defects. The defect is due to impurity in crystal. For example, in molten NaCl, if SrCl2 is present, then some of Na atoms are replaced by Sr2 plus. Each Sr2 plus replaces two Na ions. One of the site is occupied and other remains vacant. The vacancies are equal in number of Sr2 plus ions. Another example is solid solution of Cl2 and AgCl. Now moving on to non-stoichiometric defect. Non-stoichiometric defect is further subdivided into metal excess defect and metal deficiency defect. Metal excess defect is due to ionic vacancies. This is due to absence of ion from lattice site, leaving a hole which is occupied by electron to maintain electrical neutrality. The ion sites occupied by unpaired electron are called F centers. More number of F centers, more the intensity of color. Like NaCl is yellow, LiCl is pink. This is also the reason ZnO is white when cold and yellow when hot, because it loses O2 and Zn plus 2 occupies the site. Now moving on to metal deficiency. The main example of metal deficiency is FeO, ferrous oxide. This is due to absence of metal ion from its lattice site, and charge is balanced by ion having higher positive charge. Generally, transition elements exhibit these defects. FeO, ferrous oxide, is mostly found with a composition of Fe.960. It may range from Fe.930 to Fe.960. Now let's move on to last type of point defect, stoichiometric defect. They are usually of two types, vacancy defect and interstitial defect. These do not affect the stoichiometry of solid. These are called intrinsic or thermodynamic defects. These defects are shown by non-ionic solids. Vacancy defect. When some of the lattice sites are vacant, it exhibits vacancy defect. This results in decrease in density of substance. Now the second type is interstitial defect. When some of the constituent particle occupy an interstitial site, it exhibits interstitial defect. This results in increase in the density of substance. Ionic solids have to maintain electrical neutrality, so they exhibit Frenkel and Schottky defect. Now moving on to Frenkel and Schottky defect. Frenkel defect. This does not change the density of substance. This is shown by ionic solids where there is large difference in size of ion and low coordination number, which is 4 to 6. Schottky defect. Schottky defect. There are vacancies in lattice, but the electrical neutrality is maintained. This is shown by ionic solid where cation and anion are having almost equal size and high coordination number 6 to 8. Example NaCl, CaCl, AgBr and KCl. AgBr exhibit both Frankel and Schottky defect. Now this is the end of the video. So thanks for watching.